This video is about how to do the electron balance. Available electrons refers to number of electrons available for transfer to oxygen on combustion of a substance to CO2, water and nitrogen containing compounds. We have seen how much of the oxygen will be consumed during the process and how much of the carbon dioxide and heat is evolved during a particular process. So here the number of available electrons found in the organic material is calculated from the valence of various elements. In the previous video we have seen about it: 4 for carbon and 1 for hydrogen, minus 2 for oxygen, 5 for phosphorus and 6 for sulfur. So the number of available electrons for nitrogen depends on its reference state, that is minus 3 if ammonia is the reference, and 0 for molecular nitrogen N2 and 5 for nitrate. So the reference state for cell growth is usually chosen to be as same as the nitrogen source in the medium. So in this discussion, it is assumed for our convenience that ammonia is used as a nitrogen source. This can be changed easily if other nitrogen sources are employed. So do you all remember what is degree of reduction? It is defined as the number of equivalents of available electrons in the quantity of the material containing 1 gram carbon atom. So I have told you previously we have seen some examples like methanol, glucose and ethanol. In that, whatever the valence electrons, we are doing the calculation based on number of available electrons, and finally we are dividing that particular value with the number of carbon atoms, because here the definition is number of equivalents of available electron in a quantity of material containing 1 carbon atom, right? So the degree of reduction relative to the ammonia and nitrogen for several biological materials has been studied by various researchers. So the number of available electrons and the degree of reduction of carbon dioxide, H2O and ammonia will be always 0. You can check for these. Carbon dioxide, how many things you will add for carbon, and for oxygen it is it is minus 2. So carbon it is 4. So 4 minus 2 into 2 carbon atoms in the carbon dioxide. So 4 minus 4, 0. And coming to the H2O, you can see there are 2 hydrogen atoms, 2 into 1 minus 1 oxygen atom. 1 oxygen atom, what is the valence electrons? Minus 2. So 2 minus 2, 0. So for carbon dioxide, water and ammonia, the degree of reduction value will be always 0. Keep it in your mind, remember it always. So this means the stoichiometric coefficient for these compounds do not appear in the electron balance. Thus, it simplifies the balancing of calculations. So, now we are going to see how we are doing this electron balance. So, the available electrons conserved during the metabolism. In a balanced growth equation, the number of available electron is conserved by the fact that the amount of each chemical is conserved. By applying this principle, we are going to see the available electron balance equation, that is number of available electrons in the substrate plus number of available electrons in the oxygen that is consumed for the process to occur, which is equal to number of available electrons in the biomass. As we have seen, there is no degree of reduction, no available electrons for the carbon dioxide, H2O and ammonia. You remember the first initial equation what we have seen? Substrate plus oxygen consumption, which gives biomass product plus carbon dioxide, heat and water. So we are nullifying the carbon dioxide, heat and all the water. The remaining equation contains number of available electrons in the substrate plus number of available electrons in the oxygen, which is equal to number of available electrons in the biomass. So now you concentrate on the equation how the electron balance can be written. So first one is the gamma S, that is degree of reduction value of your substrate, and next is the B of 4, that is your oxygen value. Oxygen is oxygen's electron balance, and gamma b is the gram atom of your biomass, and gamma p yp will be your gram atom of your product. So if you want to calculate the oxygen demand, this is the equation you will be using. And then finally we are getting the value of b, and you are substituting the gamma s minus 4b equal to gamma b yc plus gamma p and yp, right? So you are taking the, you are dividing the whole equation by gamma s, then you will get this sixth equation, that is the fraction of electrons transferred from substrate to oxygen, and it is gamma c gamma b by gamma s, which is the fraction of available electrons for the transformation to occur from substrate to biomass. And the third one, gamma p yp by gamma s, is the fraction of available electrons for the conversion of substrate to product. So here the gamma s and gamma b and gamma p are the degrees of reduction of substrate, biomass and product respectively. You need to note one thing here: the available electron balance is not independent of complete set of elemental balances. If the stoichiometric equation is balanced in terms of each element including hydrogen and oxygen, the electron balance is simply satisfied. Okay. Here you can see the first equation, which is obtained from the previous equation, that is the fraction of available electrons for the conversion of substrate to biomass, that yc gamma b by gamma s, that is denoted by eta. So this is called energetic growth yield for the biomass. This is the formula for calculating the biomass alone. Then coming to the gamma p yp divided by gamma x, that is the free available electrons for the conversion of substrate to, not conversion, it's the transformation from the substrate to product. This epsilon p is called energetic product yield. So if any problems comes, like you need to calculate the substrate to biomass yield alone or substrate to product yield alone, means you need to use this formula here. Then coming to the next calculation, if they ask you to calculate the weight fraction of a carbon atom in a particular compound. Here I explained you with the two simple examples. For example, if I ask you to calculate the weight fraction of carbon in a particular aldehyde or alkane or organic acid, means you can do like this. For example, here I have given CH2O. So the number of carbon atoms here is 12. So if I want to calculate the weight fraction of the carbon in a particular compound, means 12 divided by the molecular weight of the remaining components. Here H2 is 2 into 1 and oxygen is 16. So 12 divided by the total amount, you will get the answer. In the similar way, whenever we are doing the biomass, microbial biomass, if they ask you to identify the particular carbon amount in the organic matter, means what we have to do? Do you remember the very first equation we have seen, the substrate plus nitrogen compound plus oxygen, which gives biomass plus product? In the left hand end I have written the same equation again, so you can able to see, right? So now if they tell me to calculate the carbon in the organic matter, so first I will take the biomass. Here you know what is the biomass equation, YCHPON So here which one is the carbon? First one. So 12 divided by 12 plus hydrogen is 1. So P. Oxygen is N. So it is 16N. And nitrogen is 14. So 14Q. So in the similar way, for the product, 12 divided by the C is 12 and HR is 1. So 1R. Oxygen is 16. So 16S. And nitrogen is 14, so 14T. And then for the substrate, it is 12 divided by 12 plus 1 M of hydrogen, so M plus 1L of oxygen. So 16L. So you need to remember these equations. If they ask you to calculate the weight fraction of the carbon atom in an organic matter, you need to calculate based on these three equations. Thank you.